Okay, in this video, we're going to go ahead and do example number 4 for the 2D force problems. This one gets a little bit more complicated because now we have forces acting at different angles. And all we need to do, though, is remember that we cannot add 30 degrees or 50 degrees, that we need to break it up into components because we can only add I hats together and J hats together. Okay, so we have a sign that hangs from two ropes, which makes an angle of 30 degrees and 50 degrees with the horizontal. If the weight of the sign is 55 newtons, what is the tension in each rope? Okay, in this sense, we have two different ropes that are holding up the sign. Or what you could say is we have the same rope that's being pulled in an angle, but those angles aren't the same. And then that means that the forces are not going to be, or the tensions are not going to be the same. Okay, so the first thing I want to do is draw a picture of this. So basically, we have a rope that makes a 30-degree angle, and we have another one that makes a 50-degree angle, and it's holding a sign of some kind. And that this sign has a weight, which is 55.0 newtons. Okay, so what we're going to do is we're going to draw our motion diagram. Well, the sign is at rest, so this makes it a little bit easy for us. Okay, so our velocity is 0, our acceleration is 0. Now what we're going to do is draw our free body diagram. What's physically touching the block? Rope 1, rope 2. Anything else physically touching? Nope, that's right. And what's acting at a distance? The Earth, that's right. Are we in equilibrium? Yes. So all three of these forces have to add up to 0. Well, that makes it kind of complicated because this problem requires us to draw it to scale with some angles going on. Okay, so let me show you my little trick on how to do this. First thing I'm going to do is I'm going to draw the weight. And I do that because that's actually the easiest thing to start with, is the weight. Okay, so there's my weight. Now, the next thing I have to do is I have to draw these lines for the ropes, and I'm going to draw them very lightly. Okay, so I'm going to use a pencil, and what I'm going to do is I'm just going to lightly draw in the rope. Okay, so there's my rope lines. Now, what I'm going to do is, this is tricky, I'm going to take my weight, okay, which I've made 2 centimeters long, and I'm going to go up 2 centimeters as a dashed line. Now, here's why I do this. Because the weight going down has to equal the tensions added together going up. And so remember back a long time ago when we were drawing forces and I showed you the parallelogram method? Well, that's what we're doing. These two forces, these two tensions have to add up to give me this amount going up, because when I add this to this, I get 0. And that's going to give us equilibrium. So we're going to go ahead and draw our parallelogram. We're going to take our ruler. We're going to slide it until we get to that line, that dashed line. Be very careful and make sure that it's actually parallel. A lot of times students just rush through this and it doesn't look right if you don't make it parallel. Okay, take this, slide it up, and there we go. Now, where these two parallel lines cross the actual rope lines, that's where our first forces are going to be. So I'm going to draw my force right here to this point, and I'm going to draw my force to here. There you go. Okay, so this is drawn to scale, and this is your free body diagram for the sign hanging from the ropes. So let's go ahead and label this. We have force on block by Earth. We have force on block by rope 1. And we have force on block by rope 2. Okay, so now we're ready to go ahead and solve the problem. what we're going to do is we're going to go ahead and write out the sum of the forces. I'm going to fold my paper because I know I'm going to be in 2 dimensions. How do I know that? They gave me an angle. Anytime they give you an angle, you're in 2D. If you're in 2D, you need x and y. Okay, so we have the sum of the forces in x is equal to ma sub x. Okay. They didn't give us the mass. They gave us the weight. So just remember that is not the mass of the block. That is the weight of the block. Be very, very careful about your units and make sure that you're actually studying this, okay? Because there's a lot of times they'll give you kilograms, and then there's other times they'll give you newtons. If they give you newtons, it's a weight. If they give you kilograms, it's a mass. And remember, mass and weight are not the same thing. Okay, so let's look at our picture. What's acting in an x direction? Nothing. There are no forces acting in the x direction. However, if you look at this picture, I do have components that are acting in the x direction. Okay, so if I draw the components of this one right here, I have an x and y component. And if I draw the components of this one, I have an x and y component. Okay, so here's the thing. This is the 30-degree angle. This is my, which one is it? It is 50 degrees. I know you're probably shouting at me through the video, and I can't hear you. Okay, so this angle is 50. That means that if I draw a horizontal line here, this is also 50. That's one of those trig things they teach you. And this is 30. Okay, so that means that this angle is a 30-degree angle and this is a 50-degree angle. So that makes it easy speasy for me. Okay, so if this is my 30-degree angle, my horizontal piece is going to be adjacent over hypotenuse. That's a cosine. If this is my 50-degree angle, this is the adjacent side. So this is adjacent over hypotenuse, which is also cosine. So I'm going to have force on block by rope 1 subscript x to show me it's in the x direction, plus force on block by rope 2 in the x direction, this piece right here, and we're going to set this equal to ma sub x. Am I accelerating, vector sign, am I accelerating in the x direction? No, there's no acceleration, Newton's first law. Okay, substituting in magnitude and direction. See these subscript x's? That tells me x component, and that means that I have to use the angle. So I'm going to go ahead and replace this. Rope 1 is going east, so that's going to be force on block by rope 1 times the cosine of theta 1, where theta 1 is equal to the 50-degree angle, and that's I hat, minus force on block by rope 2 cosine theta 2, where theta 2 is the 30-degree angle, I hat, and that's equal to 0 newtons I hat. The I hats cancel out. I could add this to the other side, and I have force on block by rope 1 cosine theta 1 is equal to force on block by rope 2 cosine theta 2. Okay, now I'm ready to do the y direction. So the sum of the forces in y is equal to ma sub y. And why am I doing that? I have 2 unknowns. Okay, adding up all the forces acting in the y direction. Now we have a y component, force in the y direction. Okay, so we're going to have force on block by rope 1 in the y direction plus force on block by rope 2 in the y direction plus force on block by earth is equal to ma sub y. Am I accelerating in the y direction? No, Newton's first law. So now we substitute in magnitude and direction. I have force on block by rope 1 sine theta 1 j hat plus force en bloc by rope 2 sine theta 2 j hat minus mg j hat equals 0 newtons j hat. Okay, the j hats all cancel out. Okay, remember these are the y components of the tension for rope 1 and rope 2. You got to have a sign if you have a subscript y. Subscript y means component. Okay, so now we have our two equations with our two unknowns. In the next video, we're going to go ahead and learn how to solve for those unknowns.